Hello, and welcome to this Luna Innovations in Maple Leaf Photonics webinar. My name is Katie, and I will be your IEEE Global Spec moderator, and I would like to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading Presentation in the upper left is the primary window for today's webinar. Just to the right of the main presentation window is the speaker bio window with background information on today's presenters. Just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed in the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. And now I would like to introduce today's presenters. With us today is Brian Solar. Brian is currently the Senior Vice President and General Manager for the Lightwave Division of Luna Innovations. Joining Brian today is Ro Hemingway. Ro is the Chief Technical Advisor with Maple Leaf Photonics. Gentlemen, welcome to today's event. And with that, I'd like to pass things along to Brian to get us started. So Brian, go right ahead.
Thanks, Katie. Thanks, everybody, for joining us for today's webinar. Today, we're going to be covering how to accelerate the development of silicon photonics and other planar integrated circuit designs through fast, accurate, and thorough testing, and specifically how that can be achieved through the combination of Luna's advanced measurement equipment and the automated testing solutions from our friends at Maple Leaf Photonics. I will kick us off with an overview of Luna's measurement solutions, and then I'll hand it over to Ro to review Maple Leaf and how the combination of our products can help you accelerate your work. Very briefly, a quick introduction to Luna. We were founded in 1990. Our headquarters is in Roanoke, Virginia. We have 280 plus employees worldwide, and we specialize in advanced fiber optic measurement and sensing solutions. So starting with a little bit of motivation for the webinar. So first of all, we're talking about silicon photonics today, but I'll add to that more broadly photonic integrated circuits. We have multiple material platforms in addition to silicon that this webinar applies to, including 3-5 semiconductors, variants of silicon like silicon nitride, silica, waveguides, and other materials. From a measurement perspective, the information we share today really applies to the broader category of photonic integrated circuits, or PICs, as well as specifically to silicon photonics. Second, we've arrived over the past few years at an inflection point in terms of the adoption of integrated optics, and in particular the use of silicon in commercial designs. The drivers of miniaturization, low cost, scalability, low power, reliability, co-integration of optics and electronics, etc., have always been there, and people have been working on integrated functionality for decades. I did my graduate work on silicon on insulator in the 90s, and all of those advantages and drivers were still there back then, and they weren't new. It's really the last few years that we've gotten out of R&D in a major way and into the mainstream with some designs that have had and seen commercial success, especially with silicon, but with others as well. We find that really compelling here at Luna. Because we're seeing that traction and commercial viability, we are aligning our product development efforts here towards making it easier and more cost-effective to develop new integrated designs. From a market and application perspective, the main driver, or one of the main drivers, at least in recent years for PICs and silicon photonics, has been communication systems. They enable getting more data with less power consumption into smaller and smaller spaces. Over the last several years, we've seen a lot of commercial progress in this space. We expect to see that trend to continue. Recent market reports show that silicon photonics will be growing at a compound growth rate of north of 20 to 25% over the next few years. So that's a healthy, growing market, and it's good to see. Certainly, many other compelling applications of silicon photonics and PICs in general that we expect to also see growing over the next few years, including military, aerospace systems, sensing systems of all sorts and all kinds of applications for sensing and miniaturizing those systems, and more exotic applications that we've been working with folks on recently, like quantum computing. As these trends continue, and specifically to the point of today's webinar, we need better ways to test our designs throughout the entire product life cycle, from early R&D all the way to full-scale production. One of the main reasons, not obviously the only reason, but one of them that we've seen this recent success in the deployment in these end markets is that we now have most of the optical functionality enabled in planar devices that used to require bulky, discrete, fiber-coupled optics. So we can do really anything we need to do, we can do it in a planar device, in silicon or in any semiconductor platform. So achieving that functionality requires not only all of the advances in design and material processing that were required, but also major advances in test techniques as well. And that's where we believe Luna comes in. So why do we need those advances in test techniques? When you look at the measurement challenge for photonic integrated circuits, it's really pretty daunting. You have all of the complexities associated with optical test in general for high-speed devices, of which there are many. And then you add to that the complexities of getting light in and out of these incredibly tiny devices that are embedded in a chip or a wafer and in a material with a significant index contrast to glass and in a geometry that does not match fiber optics, planar geometry. So all of this amounts to a really big challenge and the need to develop test strategies very early in your process of either research or product design to ensure success. In addition, these challenges add up to test being one of the largest cost contributors to developing an integrated device, and that's shown here on the graph from an IEEE study from last year. So it's really critical to get it right, the test side. And it can really make all the difference between a successful project and a big waste of time and money. Ro will talk about getting light in and out of the chip or the wafer or the die. But even with an elegant solution to that problem, which he will cover, there are some really unique challenges to properly characterizing PICs. And that's where we know Luna can be of help. So how is that? How can Luna be of help? Well, we manufacture test equipment that incorporates the most important elements of tests for photonic integrated circuits. Completeness of test, accuracy, and speed. We also have products that give you unprecedented visibility into your photonic designs. So that will help you make sure your device is doing what it was designed to do, and equally importantly, that your process is dialed in. One of the things that can tend to get a little bit lost in the conversation is that we optical people don't always fully appreciate the statistical nature of semiconductor processes, and that a lot of test is required to ensure success over time. And when a lot of test is required, that's where you need to make sure you're doing it accurately and you're doing it fast. So given how the costs can build up and they can rise, especially for modification over time, and the later you get in your process, really the key takeaway from this slide is to test early, test thoroughly, and test often. And that's where Luna comes in. We have a full complement of test equipment for the entire life cycle of an integrated optical device development, from R&D all the way through to full-scale production, including single function test equipment and analyzers for polarization, a line of reflectometers, and a full-scale component analyzers. For the webinar today, I'm going to cover the three here that I've highlighted in blue: our optical backscatter reflectometer, which kind of comes in the early stage, kind of an R&D kind of stage tool, development tool. And then we'll talk about the OVA, which gets us kind of bridge the gap between R&D and production. And our newest product for this category, our lightweight component analyzer, which is really aimed at more of the production type environments. Won't spend too much time on this, but at Luna we've developed a really unique core technology called OFDR, Optical Frequency Domain Reflectometry. We've built a significant IP portfolio around this and set of know-how that it's enabled us to bring the functionality you're about to see to market. And this is a pretty unique technique that combines a tunable laser with an interferometer to probe optical systems with very, very high resolution, very high speed, and very high sensitivity. So the first product I'd like to talk about is our optical backscatter reflectometer, model 4600. This is our ultra-high resolution reflectometer for optical components and short networks. So when I say ultra-high resolution, I mean spatial resolution of 10 micrometers or better. In fact, that 10 micrometers is in glass. So for components in short networks, that's over ranges of anything from a centimeter up to several kilometers. Very high sensitivity, 130 dB noise floor, a wide dynamic range, and it allows you to analyze the reflections in a device over length. And in particular, with the very high resolution and high sensitivity, it allows you to see not only reflective events, but non-reflective loss events because it has backscatter level sensitivity. So you can actually see the scatter in a waveguide, which tends to be a very, very weak signal. So the first example I'm going to give is an interesting device. It is from our friends at University of California, Santa Barbara, whom we've worked with for many years. And it's a 1 meter delay line in silicon nitride. So before I mentioned, we've got most or all of the functionality we need in integrated devices. I'll say the one thing that is very difficult, though, to achieve in such a small footprint is things like delay. And so if you need longer delay lines, that's something that has to occur off-chip. But people are making progress, and in this case, we have about a 1 meter delay developed in silicon nitride. If you look at the pink mask layout there, you see on the right side, you'll see a waveguide trace entering from the right at about the middle, and then it crosses a circle, and then it goes up and to the right, and it goes into a spiral. And the spiral crosses the entry waveguide every revolution until eventually you get to the outside of the spiral, and you can get back off the chip. So what you're looking at in the result is an example of how you get unprecedented visibility with OBR technology. Along the bottom axis, if you're looking at the graph, is length, and we're showing about a meter, a little more than a meter of length. And on the left axis is reflectance, dB. So it's a negative number in its reflectance. And you can see at on the left side, you see a Fresnel reflection, which is the interface to the outside world. So it's fiber coupled from the edge. And you see what you might expect is just a peak, a localized peak, and that's a Fresnel reflection. But then once you get into the waveguide, you see a lot of very interesting things. First of all, you see the waveguide scatter. Prior to that first reflection, you're actually seeing the waveguide scatter from the input fiber optic lead. Then you see the interface, and then you see a jump up in the scatter level. That's because this waveguide scatters with a backscatter coefficient, which is stronger than that of a single-mode fiber. And then on top of that decay there, you see a series of peaks. Each one of those peaks is when the waveguide crosses itself, and when you get a waveguide crossing like that, you get scattering, so you can measure all of those. You see one peak that's a little taller than the rest, and that is a probable defect, a scattering event that wasn't designed. And that would be basically impossible to see with any other technique because these are such small reflections. And then all the way out at the end, you see the end of the device. So you can see a lot of really interesting behavior here. And like we like to say, you can't fix your design if you can't see it. So this is an example of how you can really see into your design. If we click and just now say, let's look at this very small section at the front of the waveguide, and let's inspect that in high resolution. Now, all of this data is already in high resolution, but we're just going to zoom in on it. So this is about 3.5 millimeters zoomed in to that what looked like one reflection, and it's actually a facet reflection there on the left. So that's the input coupling. And then there's waveguide scatter. And then you get a 2 millimeter section where you see about 50 individual scattering events. And that's where that input waveguide is actually crossing over all of the different spirals leading in. Having the high resolution really enables you to dig in and see what's happening in your device. So this, as I said, especially in the early stages of development and design, you really need to be able to see into what's happening in your device, and the OVR really gives you that visibility. Okay, so moving on, the next product we'll talk about, the Optical Vector Analyzer, OVA. This is our high-speed integrated all-parameter analyzer for optical components. So by all parameter, I mean it measures all of the relevant parameters of a passive device. So insertion loss, return loss, PDL, it measures phase, so group delay, chromatic dispersion, it measures birefringence, which is important for communication systems in terms of PMD or differential group delay, DGD, Jones matrix, etc. You can think of this as the equivalent of RF vector network analyzer for optics. When building up test capability, typically one starts with, conceptually anyway, well, I need a laser source. So I start with a laser source that covers the relevant bands and then builds from there. And then what do I add to that laser source? Often that laser source is a big investment. But in dealing with high-speed devices in silicon and in PICs, you can't just measure amplitude and loss. You need to build upon that. So in addition, you can add some polarization control, some polarization analysis. You might need to measure phase at some point, etc. And you can see the point of this graphic is that the OVA really removes a lot of this complexity by integrating all of this test capability into a single instrument. So if we take an example here of the OVA, the first example for all parameter characterization here is of a narrow channel optical filter, a type of filter that would be implemented in a communication system. So what you're seeing is a 20 nanometer scan, and you measure all of the information there, not only the channel insertion loss, there you see on the left and the upper, but the in-band PDL, the in-band birefringence, and the in-band phase or group delay. The advantage the OVA brings is it has that internal tunable laser already integrated, and it has all of the other measurement capability already integrated, and you have access to all of this data in this case less than a second. And importantly, you'll note my very simple looking graphic there. It can be integrated with a probe station, and Ro will talk more about that very easily. And what you'll notice we don't have there is a polarization controller. The OVA removes the need for use of a polarization controller at the input of a device. And that's really important because it makes it much, much easier to analyze, especially planar devices that would otherwise require that. And I'll talk more on the next slide about why that is. But the OVA essentially launches all of the polarization states into a device, and then you, as the user, can choose which ones you're interested in. So if you only want TE or TM, you don't need to worry about it. You just hook up, scan, and then you can extract the TE response from the data. You can extract the TM response from the data, or the fast state, or the slow state. One other quick key here is that just measuring the filter shape of this type of a filter, or really just measuring the loss of any high-speed device is definitely not enough to characterize the device. To really characterize what the effective bandwidth of this filter is, you need to measure all of these parameters and how they work in concert. As an example, we're working with a customer right now that was really seeing huge variations in the ODE bandwidth of a new 25 gig design, and they were seeing things, they were seeing bandwidths between 15 and 25 gig chip-to-chip variation for the same exact design. And what it came down to was there was a variable process issue that only showed up in the phase measurements. So it was really a group delay phase ripple issue that was causing these strange bandwidth results. And you would never be able to unearth that without really this completeness of test. This is why we stress completeness of test. And of course, this is also a very fast test, but you can get a lot of testing done in a shorter amount of time. If you're probing even just test devices die at the wafer level, you don't want to spend 24 hours testing one wafer. You need to be able to get through it quickly. So we stress that you need to be well under 1 second per test, if not faster than that. The next example, I'm just showing characterization again from a device from our friends at UCSB. This is a grading device built into a straight waveguide. And this is a reflection mode scan with the OVA. And what I'd like to show here is to highlight that point that you don't necessarily always need to control the polarization into the device. First thing with this device is if you look at the lower left, you see a red line, and it's a broad band reflection at about 20 dB. Well, that's the facet interface. What the OVA allows you to do, if you go look to the right in the upper graph, the red I've highlighted there, those are the facets. We can actually filter those out. So the OVA has software that allows you to say, I don't want to see the facet reflections. So I filter the facet reflections out, and then I get the blue curve. If you go back to the left and you look at the blue curve with the two peaks, that's the grading reflection from within the waveguide. And I can see I've got two reflections from the same grading. So what's happening here? Well, this waveguide was engineered to have a lot of birefringence in it. And birefringence leads to differential group delay or PMD. It also leads to spectral splitting of things like filters. And so this one bright grading is actually split into two based on these two different polarization modes. And with the OVA, I can very easily, if you go down to the bottom right and look at that curve, isolate the reflection of either the TE mode or the TM mode without having to go through the physical selection of those modes at the input, which saves a ton of time, and it really removes complexity from this test. And lastly, I'll talk about our newest product, as I mentioned, a little bit more for production environments. This is our 6415 analyzer, and what we're going to do is we'll show a quick demo of this measuring an integrated device. It's an interesting device. It's an array of 1x2 couplers. So there are 16 1x2 couplers in this array integrated into a silicon platform, and they're all in a very small space, as you can see. And we're going to look through one of the channels to see what we can see with the 6415 analyzer. So this is the interface to the 6415. Just get it going here. And right now nothing's connected, but we're going to go ahead and connect this planar device and make a scan. And what you'll see is now you can see the device. So there it is. This is in reflection. So now you're locating it in space. So there's a fiber lead, and now here we're looking inside the device itself. So on the left axis is reflectance, on the bottom axis is length. And I can go ahead and hit continuous scan, and you see here this system scans at about 6 scans per second or so. Bring up a cursor and highlight the input reflection. In the upper left, you see that's about a 59 dB return loss, and I can look at the output reflections as well. Remember, this is a 1x2 coupler, so there's an input reflection. There's all the waveguide scatter in the middle there, and then it's 1x2, so there's the two output lengths inside the chip have the two output paths have slightly different lengths. So that's why you're seeing them in slightly different location. And in between, you're again seeing waveguide crosses where when the paths cross, you see a little spike with scatter. Should say that those are grating coupled as well. So you have a fiber optic coming into a surface grating coupler into the device, and then 2 grating couplers out. We can look at the spectral content. So now I can choose just this peak, and I can look at its spectral content on the bottom. So you can see that's about a 30 nanometer scan, and it has some. It's fairly broad, but it does have some spectral content, and that's really the spectral content of the grating coupler. And I can use some cursors to go find locations and values in reflection. When I move into the waveguide, I see just the scatter of the waveguide. And then on the end, if I highlight both reflections, I see the broadband. And then if I just highlight one, I see, if I highlight both, I can see the interference between the two. And if I highlight them separately, again, I'm just seeing now the grating coupler. So that just gives you an idea of some of the fast, accurate data you can extract from a device. So this would be used, to qualify, very quickly qualify the RL of as many devices as possible over time. Okay. All right. So just to sum up my portion here, characterization of any optical device can be complex and costly, but planar waveguide devices present some also additional very specific challenges. So at Luna, we have tools that can help you maximize your designs and lower the cost and complexity of test. And with that, we will switch gears. I'll hand it over to Ro to talk about Maple Leaf's offerings and to talk about how we get light in and out of the die and how we can integrate test equipment with probe equipment.
Thank you very much, Brian and Katie. I appreciate you all being here. I know some of you are calling in from far away. It's really been a delight to be working with Luna on this activity because their machines are really astounding in terms of what they provide in terms of insight to the chips. And what I'd like to talk about regarding the optical probe stations is how do you attach these wonderful high-resolution instruments to your chip when your chip is either in a wafer form or a die or even on a submount or on an eval board. How can you set it up to probe your device and even configure your device and even calibrate it or tune it up as part of the characterization? And the emphasis that we would like to establish here is that the earlier you do this in your fabrication process and in your development process, the more insight you get into the role of fab variations. As Brian pointed out, Silicon Photonics in particular is very statistical in nature. 50-50 couplers are only 50-50 if the fab is correct. And the idea here is to get as early a view as you can of the performance of the circuit and ensure that any subsequent processing you might do is also maintaining the fidelity that you got up front. And so what we'd like to point out is that you sometimes need to bring in high-frequency signals, you need to bring in DC bias, and a probe station lets you not only connect the optics, but also to set the configuration of the chip itself. And the earlier you can do that, the more insight and the more data you can get. And automating this, of course, is a big part of success because you need a lot of data to get a statistical understanding. There are variations from wafer to wafer or run to run. And you need this information to establish your yield profiles and focus your engineering resources to address the issues that pop up. And what's nice about this configuration of equipment, Luna's OBR and the OVA, together with Maple Leaf's optical probe stations, is that you can bring these tools to bear throughout the life of the development cycle of your product. But in particular, you can bring it early in the process, and that gives you insights that allows you to make decisions that you otherwise could not do. So with that as an intro, let's get to an understanding of what's involved with these chips. A silicon wafer today, a silicon optical wafer, has many, many different components in it. Couplers, ring resonators, Mach-Zenders. Often it has a place for lasers to be put on with tuning elements. You have ingress, you have to get light into this thing and out, either typically from an edge coupler or an evanescent coupler or a vertical grating coupler. And a probe station needs to be able to provide both optical access to the chip as well as all the electrical access needed to configure the chip during the testing. And oftentimes you don't have much power, so you need high dynamic range, and the Luna products provide more than 80 dB in some cases of dynamic range, and can do so with just a few instruments, or just one instrument. And that simplifies your process. It doesn't take much time to integrate the tools together in your automatic test environment. And by applying this early in your development cycle, you get that insight as soon as possible. But there's some challenges. Obviously, you need to be able to characterize the process parameters of are the gratings the right pitch and the right contrast ratio? Are the critical dimensions of your waveguides correct? Is the photomask accurate? Did you have errors in it? Because you wouldn't like to be able to process a wafer if you find an error in the silicon layer, because there's a lot of additional processing that occurs for doping and germanium and metals that you may not need to do if you find out there's a significant error in the bare silicon layers. Bringing these tools to bear, you want to be able to also track how does the process of fab change the behavior of the chip. So you may have strain. If you have a silicon nitride layer, strain management is a good example, a big challenge. You'd like to see where is the strain being introduced and can it be relieved. The tools that we've described already provide that, and by being able to make measurements throughout the cycle of wafer fab, back-end process, singulation, sub-mounting, and eval board, and making the same kind of measurements throughout that chain of activity, you can get a great insight into where stresses are coming up, where aging effects or humidity effects are having a problem. And so this is why these types of tests give you insight that is very difficult to get otherwise. So if you succeed in this, you save a lot of time, you save a lot of money, and you get great insight. You eliminate bad wafer runs because you can establish the fidelity of the patterned silicon layer without having to go through subsequent metal or doping profiles. You can just establish that the silicon layer is correct. You obviously don't want to do that with a wafer you're going to put back in the fab. So it's important to maybe add an additional wafer or two in your batch so you can pull out a wafer to characterize it early, since most fabs won't let you reinsert a wafer. This automation then gives your engineers time to analyze the results rather than take time measuring results. If you do this by hand, it can take weeks, if not months, to fully characterize a wafer with thousands of circuits on it. And so automating this task and putting it into a big data analysis system gives your engineers the real insight that they need to know that statistically you're on the right track. So the probe stations that Maple Leaf has developed have to be able to do a number of things. They have to be able to provide damage-free access from edge and the vertical coupling into the chip. You need to be able to provide bias conditions for photodiodes and heaters and other and diode elements on the chip with integrated source measurement units, and also provide DC and RF inputs. So you can imagine there's a lot of congestion around the chip that has to be accommodated. And in this picture, you can see that there's a fiber array, and it's very important that that fiber array, as it's manipulating around the chip to pick up different grating couplers, doesn't bump into the electrical leads. And so you need software and keep out areas and so forth to assure that. And of course, as you get through your process, you may start with a multi-project wafer, which is a discrete die. Typically, you get discrete die from the multi-project wafer team, and you make measurements on that. As you get going, you're going to be bringing home whole wafers, and you want to be able to characterize the circuits in the whole wafer form. And then as you ramp production and you begin looking for access to the edge of the chip, going into a multi-die testing is nice too, because then you can characterize a bunch of discrete dies that have been singulated, and you can do that automatically without having to have high cost engineering resources dedicated to the task. And a probe station that does this well will control the environment, certainly temperature, and in some cases the cover gas, especially as you get below the dew point. And then because these circuits are so complex, it's important that the test equipment be able to make a measurement of the configuration state of the chip and then tune that configuration before making a measurement. For example, in some of the backscatter measurements that Brian talked about, you can't actually see down certain paths of your chip unless you configure them first. So having a test equipment that has the ability to monitor either an on-chip photodiode or perhaps an external photocurrent, an external power meter to be able to tune up ring resonators or Mach-Zenders, either for peak or for null, and thus configure the internal state of this complex circuit so that you sequentially go down a line, sequentially illuminating the parts of the circuit that you want to test. And so having a test system that understands that and then intelligently configures the chip is a very important part of success. And then finally, of course, you want to automate this and integrate it with your environment. You may want to run scripts, very complex testing scripts. And so the test equipment, whether it's a Luna OBR or OVA or Maple Leaf software, you want to make sure you have scripting capability and APIs that lets you connect the test equipment to your test environment. So Maple Leaf's approach is kind of unique in this world. We really are focused on the RD&E community, not production. And the idea here is that we have to deal with lots of different configurations of the die. And so we start with a very modular platform. Off to the left here, we generally start with the chip stage, and that determines how many chips or whether it's a wafer form or multi-die carrier. That pretty much establishes the range of motion that's required out of the probe station. In addition, we have the fiber aligners. All our fiber aligners can either do both vertical coupling as well as edge coupling. You just flip it over. And we provide a mechanism, either automated or manual, for bringing in DC leads for biasing circuits and measuring photocurrents and other attributes, voltages, and so forth, using very sensitive source measurement units. But in addition, you have to be able to bring in RF probe leads as well. And so in a probe station of this kind, you typically would have a handful of RF probes, maybe 24 high frequency probes, millimeter wave or so. If you need more than that, we'll talk about how you can get there as well with these probe stations. And then separately, we have optics to enable you to look at have a view of what's going on at the chip level and make sure you're aligned appropriately and the system is behaving as expected. These are all controlled with control modules. They're configured depending on your needs. All the systems come with a system controller and a motion controller. But we also offer some photonic elements which can control polarization beyond that which Luna provides. We have a laser as well, and the photodetectors in that environment, and switches, so we can switch in and out different test equipment and configure it very flexibly. And then an environmental control module, which is largely responsible for setting the temperature of the chip, but can also be used for other purposes. And so this is all wrapped up in Maple Leaf Photonics software. It implements not only fast optical alignment algorithms and controlling instruments, it also offers scripts and an API for you to be able to set it up with your test environment and succeed with automated testing with scripts that you write and an environment that you already have in your lab. Optical equipment's expensive, and this approach allows you to take advantage of the infrastructure you already have. So Maple Leaf's optical probe station is simple in concept. We have a base plate and a platen, and typically we select a chip stage, which in this example is a manual stage, which might be appropriate for a university starting out with a multi-project wafer. You can, of course, upgrade these to a motion stage for both chips as well as wafers. There's a fiber aligner, and this is an example of a very fast alignment algorithm, a system which can acquire and do a fine align in just a few seconds. This particular one is set up for vertical coupling, but you can just flip that element over to achieve edge coupling as well. We also have various side view and top view optics. The side view optics travel with, the top view optics travel with the moving fiber array. In this case, it's a vertical alignment, so you can then scan over a two-dimensional surface of your chip to pick up all the grading couplers that require attention. In this simple system, we have only a system control module and a motion control module, but you can add environmental and photonic modules as well. So as we learned, some of the critical tests that you would want to implement really have to do with what's going on at that silicon layer. And with Luna products, you can do these measurements entirely optically. And what you learn is the waveguide roughness from your lithography. You can establish the polarization behavior of your passive circuits. establish whether the critical dimensions and the submicron gaps between waveguides for couplers are accurate. Look at 50-50 couplers and make sure they're 50-50, not 49-51. A really powerful insight comes from measuring the extinction ratio of ring resonators and Mach-Zenders. That also gives you key insight into the lithography, as well as the wavelength dependence of these. And with loss and bias conditions, you can measure the doping fidelity and ensure that your junctions are where they need to be in your process. Some foundries will let you have access to their process control module, and you can use these tools to verify that the foundry achieved its critical dimensions. You can compare your results with what the foundry measured if there should be a question sometime later in the process. And then I'd like to spend a little time on what happens when you take advantage of these for doing partial or split wafer runs, where you submit a batch of wafers for fab larger than what you'll end up with, but you then use measurements during the fab process to down select and fine-tune your output. You wouldn't be using this for production, of course, but you would be using it for helping you develop and fine-tune your development activity. So what you can think of these probe stations, what are they doing? They really are connecting the optical test equipment like the OBR and the OVA to your chip. And your chip can be either in a wafer form, a partially processed wafer form, a fully processed wafer, a singulated die, which would be a part of that processed wafer, or as you begin wanting to do higher orders of automation using multiple die testing. And then, as I mentioned before, being able to do a test with your die already mounted on a submount, maybe with many high-frequency bonds on it, going with integrated drivers and control electronics. These sorts of test probe stations are designed to support all of those chip configurations. And so if we start with what a partially processed wafer looks like, this can be very helpful early when you're early in the fab process. You pull a wafer out of the fab that just has patterned silicon on it and maybe a cladding, silica cladding on it. It won't have metal, it won't have doping, it won't have germanium, but you can use the all-optical test equipment of Luna together with a Maple Leaf probe station using surface grading couplers to characterize the state, the internal state, the passive state of the optical circuit. You can make sure that the losses are correct. You can make sure the backscatter is correct. If you see crossed waveguides, you can evaluate their crossing. And if it turns out that something is off or off by enough, you may choose to halt the run and start over again. And you don't have to process the entire wafer to get this insight. Unfortunately, when you're going to do it this way, you can only have optical access to the chip. So you aren't going to have the metals that would allow you to bias things up. So it's really a passive view in, but it's a very early passive view, and you can save a lot of energy and time if you find something's wrong at that level. Once you have a fully processed wafer, of course, you can do full OE test, both DC and RF. You can use the surface grading couplers, of course, and we continue to. Edge couplers really aren't available at this level unless you have a deep etch process. And yes, you can do that, and we have, in fact, done that with some processes. But the favored places, the favored ingress and egress is using grading couplers. But keep in mind that they tend to have polarization dependence that you may not want in your product. So people very quickly migrate to edge couplers, and that generally requires singulated die. But the advantage of working with a full wafer after it's been fully processed is that you have photodiodes that are available for you to do biasing on. You can monitor dark currents and tune things up. You can validate your doping levels by biasing photodiodes, measuring capacitance and loss. And you can also characterize devices so you don't process any further if you see some defects. So you don't spend money mounting something up or characterizing as a singulated die. You can simply essentially logically ink them out if you find there's something wrong with them. Some folks, by the way, find it helpful to take a partially processed wafer and then just change the metallization for a subsequent test or subsequent processing to hook up different devices. For example, they may have enough electrical probes, bond pads for only, say, 1,000 devices, but they'll put 4,000 on the wafer. And what they'll do is make a measurement of the passive devices to make sure they know which set of 1,000 to hook up. That requires a lot of agility on the part of the project team, but it's a way of getting a lot of insight and being adaptable to the variations that come from the fab. Once you have a singulated die, you have more control. It's a more realistic environment. You can bring in the full OE tests and bring drivers up close to the chip and so forth if you're running at high frequencies. You often work in this environment to develop further your tests that you want to implement for either device qualification or for full RF testing. And the real advantage here is that you get access to the edge couplers, which are the lower loss and wideband couplers that enable you to get the maximum performance out of your chips. There are very good vertical grading couplers out there, but the edge couplers seem to be what people migrate to once they know what they're looking for. In the multiple die environment, this is when you begin ramping up for production, and you want to be able to have a lot more automated testing without having an engineer manually or technician manually load and unload discrete die. And Maple Leaf has a number of multi-die carriers that we've developed that help with this. 16 chips is a pretty common number. And the idea here is you use it for qualification. You have, again, access to the edge and grading couplers, but you get the benefit of being able to fully characterize the die without having to mount it on a submount or do a fiber attach. You can simply characterize the device, establish that it's good, and not spend money or time trying to mount it on something else unless it's known to be good. So the idea of don't process bad material is really helpful in this environment. And then last but not least, when you have the die on a submount or you choose to put it on an eval board or a PCB, you can really now bring all the environment that chip is designed for, whether it's hundreds or even thousands of wire bonds or solder bumps, bring in laser sources if they're available there, drivers both on the transmit and receive side, as well as switching elements for Mach-Zenders and ring resonators. And all of these can be integrated on an eval board or a PCB, and the optical probe station, when it's configured correctly, can allow you to have optical access to this as well. And so again, you don't have to have the fiber attach or invest in packaging or a full module in order to adequately characterize the part. If you step back and take a look at this as a whole, what you are seeing now is you can identify what each of the steps in manufacturing does to your chip. If there's a change in stress due to a die bonding process, solder, say, or glue or epoxy, you'll see it and can, I'm sorry, I'm trying to skip here. And you can see it as your process flows. And so you can compare the performance in wafer form versus singulated die, or in a submount after the singulated die, and you can see what the effects are of those processes on your chip. And the Maple Leaf probe station really gives you access to this entire set of configurations, and will hook up not only the Luna OBR and OVA products, but also any other systems that you might have. You may have microwave spectrum network analyzers or a full computerized system that you want to attach. The probe station really is designed to give you that connectivity and help orchestrate the testing that you would want. And so to tie this all together, both Luna and Maple Leaf provide pretty extensive software interfaces that embody a lot of embedded control within each environment, and then interfaces that allow them to be controlled or to control others. So Maple Leaf has APIs and a scripting interface that allows a very efficient connection to the Luna products. And then Maple Leaf also provides these interfaces and can provide these interfaces to the customer so we can integrate with your established automatic test and measurement environment. And by having this flexibility, it becomes very easy for you to get the insight you need in your process and on your development activity throughout the life cycle of your development program. So I just want to wrap up here. Clearly, Luna and Maple Leaf have products that work well together. Luna's OVA 5000 vector analyzer is unique in terms of its spatial resolution. It gives you incredible insight into the chips, and it replaces several optical instruments with one. You don't need the polarization controllers. You don't need the power meter or the tunable laser. It's all built in. So one instrument does a lot, and the same is true with the Maple Leaf product. We connect to these products. We have source and measurement units that allow you to stimulate and set the configuration of dozens of internal parts within the circuit to tune them up and to set them to their operational state, and can automate the process of characterizing them once that's been done. You can characterize partial and fully processed wafers, singulated die, and multiple die in a carrier, as well as die on a submount and an eval board. And the point here is you want to be able to halt bad wafer runs, you want to track the impact of process variations, and eliminate on the back end costly assemblies and fiber attach operations that aren't needed to establish the fidelity of your device. So to summarize, early and complete insight into process fidelity, the critical dimensions of your fab, your circuit design, and device performance, you're going to save time, you're going to save cost, and you're going to get insight that you can't get otherwise. So with that, I'd like to thank you for attending our webinar today. Thank Brian and Katie for setting us up, and I believe we are off to another phase of question and answer.
Yes, thank you so much. So gentlemen, thank you so much for your great presentation, Brian and Ro. We do have questions that have come in from the attendees, and we are going to move into answering those right now. For the attendees, if you have a question, go ahead and place it into the Q&A window and click submit. And if we don't have time for your question today, do not worry. We will answer you following the webinar today. We have about 10 minutes for Q&A, so we're going to get right into them. Brian, I'm going to start off with a question for you. How do you manage polarization into and out of the wafer or die? Yeah,
so great question. I hit on that a little bit during the slide portion of the presentation. So for the OVA, as I said, we recommend single mode fiber, and the OVA actually pushes all polarizations through, and then you can actually extract from the data any of the principal states or polarization modes that you're interested in. So for instance, if you only want TE, you can actually extract it from the data. And I believe we have an app note on that that I can make sure we publish the location of. For the OBR is a little different. It uses one polarization state only. So what we recommend there, if you really need to make sure you're launching a specific state, is you can marry that with one of our polarization controllers from our General Photonics product catalog, or you can include the addition of polarization maintaining fiber, and just make sure you're aligning to one of the modes of that fiber, and then you'll get say linear polarization out at the device.
Okay, great. Thank you so much for that answer. Ro, I'm going to move into a question for you. Can you configure the optical circuit by setting detailed bias conditions as part of the circuit characterization, and how?
Great question. Thank you, Katie. You can set the configuration of the circuit only if you have access to the control leads that do the job. Maple Leaf offers a set of source measurement units which can provide either current or voltage, or use 4-point techniques, 4-point probe techniques, to monitor and set the bias, current or bias voltage on an internal device, down to, I believe, the nanoamperes of resolution. So by having dozens of these source measurement units, you can sequentially tune up ring resonators, Mach-Zenders, and others to establish the circuit connectivity that's needed within either a quantum circuit or a transmitter circuit, for example, or a switch. And then once you have those paths established, you can then illuminate or complete the characterization. So typically you start with a light source and sequentially illuminate the path that you want to characterize by monitoring photodiodes and looking at outputs And as you think about your layout, and you think about how you're going to design these complex circuits, it's very important for you to consider how you're going to configure this before you test it, because it often doesn't make sense to test a circuit that hasn't been configured.
Okay, great. Thank you so much for that answer. For all the attendees, if we don't get to your question, this is just a reminder, we will reach out to you following the webinar. Next question here, guys. How are the Jones matrix parameters extracted by the OVA 5000 normalized?
This is Brian. The OVA is calibrated. It requires a calibration for amplitude or for loss. It doesn't require a calibration for the phase measurements or polarization. That's all handled internally. But for the loss parameters, so the Jones matrix amplitudes, you have to give the analyzer a calibration path. So you can do that just by shorting the output to the input and calibrating, and that normalizes all those parameters. For this type of device characterization, you can typically you just design in a short into the waveguide device and send the probe station to that path, calibrate there, and then you're calibrated for all the losses included in that path. That calibration step takes about 1 minute, but once you do it, we recommend you do it about 1 time per day. So once you do it, you're calibrated for that whole day.
Okay, great. Thank you so much for that answer, Brian. We do have time for, I believe, 2 more questions before we wrap up the webinar. So, Ro, this one is for you. What are typical alignment time and accuracy?
That's a great question. So our system establishes a coordinate transformation between the chip surface or the wafer surface and the coordinate system used by the optical probe station. And that takes a few minutes, typically 5 or 10 minutes to set up at the beginning of a test run. And then once you have that and it's established what X, Y, and Z is and planarity, then it becomes a very simple task for the system to scan over and pick up and log the location of all the grating couplers or edge couplers in the chip. Typically, we would upload a GDS from your design file to tell the system where all these grating couplers are, and it will simply go to those points. Once it's in the region of the correct point, it will simply do a quick sub-10 seconds final line scan to pick up the actual grating coupler sets that you're looking to accomplish. But it's that first alignment and coordination check takes a few minutes, but then once you have it set up, you can measure thousands of devices with just a few seconds between each of the measurements. And I'd just like to point out that with the Luna measurement equipment that can make very sophisticated measurements in under a second, you really do have the ability to measure tens of thousands of devices in a wafer very, very quickly.
All right, great. Thank you for that answer, Ro. So this is going to be our last question for today. If you do have a question for either Brian or Ro, please enter it into the QA window and click Submit, and we will get back to you following the webinar. So, gentlemen, the last question today, can OVA do the job as OFDR?
Yeah, so that's a good question, and we get this a lot. What are the different, you've got OFDR as a technology, then you've got OVA as a product, and OVR as a product. They're both OFDR technologies. The OVA is designed to measure strong signals and things that are transmitting or reflecting a lot of light. And it includes all of the polarization analysis. Okay, so you can use it in reflection or transmission. The OBR is designed to measure very weak signals. So it's on the other end of that spectrum, and it's only in reflection. So the OBR measures only in reflection, but it has very, very high sensitivity. So it can measure scatter because it's designed for small reflections. The OVA does not have that level of sensitivity because it's designed to measure strong signals. So they both do OFDR. The OVA does it with all polarization automatically handled, but it cannot measure scatter, which is important for waveguides. Whereas the OBR is doing OFDR. It does not have all of the polarization handled automatically, and it's designed to measure scatter. So that's really the difference. You end up using them very differently, but they do both draw on the same core technology.
Okay, great. Thank you so much, Brian, for that last answer. And we are going to wrap the webinar up right there. We're right at the top of the hour. So I just want to say thank you to Brian and Ro for a great presentation and for taking time to be here with all of us today. So thank you, guys.
Absolutely welcome. Thank you.
Yep, thank you very much.
All right, thank you, guys. And thank you to all the audience members for being part of this webinar event. A couple of people are asking about the PowerPoint. Along the bottom of your webinar console, there are some widgets. In the resource widget, there is a PDF version of the PowerPoint if you'd like to download it there. And there's also another nice PDF in there that you can take a look at. So take a peek at the resource widget before you leave. And lastly, if you would like to please take the survey that's going to appear on your screen at the end of this webinar. For anyone that's going to watch this again later on demand, the survey will be in the survey widget located along the bottom of your attendee console. Thank you, everybody, for being here today. You are going to receive an email from us with a link to the on-demand version of this presentation, so you are able to come back and watch this again and share it with colleagues. And thank you so much for attending our webinar event today. Take care, and we will talk with you soon.